All right, so I'm going to go through these steps. So, in fact, I feel kind of bad. I didn't. Okay, maybe I'll write them up here real quick. Horizontal, oblique. They're supposed to be in the notes now. I don't got time for that. I'm just going to forget it. So I'll just write a note. I'll just write a note for anybody watching this to see instructions. Go to the Math 4B Tuesday, Thursday lecture on 4.2. All right, enough said. So go there if you're watching this to the other lecture, other class. All right, so let's do it. So how do we find it? So we take, what's the numerator degree? We're finding the horizontal or oblique asymptotes right now. What's the numerator degree? 1. Denominator is 1. Yeah, in a minute. I'm going to let everybody get that. Can you look over here for a second? So numerator degree is 1. Denominator degree is 1. So that means they're equal. So that's what? When they're equal, you've got a horizontal asymptote that is y equals. That is y equals a over b, which is, what's a? 12. B is 1. 12 over 1. The leading coefficients, right? I mean, the numbers in front of the most powerful terms. 12 over 1 or 12. So y equals 12 is the horizontal asymptote. Is that good? I haven't given any logical reasons for that, but maybe if time allows I will. But let's keep moving. Whoops. All right. All right, so got y equals x squared over x to the 4th minus 16. Remember how I said so let's do the vertical first off. So for the vertical asymptotes, what I said is, number one, you should try to factor and reduce if possible. I'm not going to do that. Having said that, this one's not going to. Can you see it coming? I mean, you could factor that bottom, x squared plus 4, x squared minus 4. Then you can break down the minus, not the plus, right? So x plus 2, x minus 2. It's never going to cancel with anything in the numerator. It's never going to. So let's don't bother, right? Let's don't bother. You only mess with that if something's going to cancel. Something's going to reduce. But it will not, right? Having said that, maybe I should. Right? You would do this. Don't even do this, even though I'm doing it. Right? And then this guy can break down. The other guy may not. Remember? Double plus. Can't go anywhere. So this would be x plus 2, x minus 2. The other guy would just stay as he is, x squared plus 4. See, nothing cancels, so who cares? So skip the whole thing. All right? So normally we skip that step 1. It's very rare that something cancels. Step 2, what do? Denom equal to 0 and solve. So let's do it. What's the denom? X to the 4th minus 16 equal to 0. Solve it. How do I solve it? Yeah, well, yeah. Well, you could. We could just move the 16 over and then 4th root it, Right? Why don't we just do that? Might be. You could factor it, though. Like Robert said, it's totally true as well. Now, remember, whenever you put an even root, you got to do plus or minus, huh? Right? So you get x equals, what's the 4th root of 16? Well, it's 2. It's plus or minus 2. Which factoring would tell you those answers as well? So plus or minus 2. Those are the vertical asymptotes. X equals plus 2, x equals minus 2. In other words, if you were to draw a graph, there'd be one over at positive 2. There'd be one back at negative 2 on a graph. Make sense? Got to get the horizontal now. So let's go to the next part. All right, so now it's horizontal, oblique. We do them together. All right, what do? We take the numerator degree, which is 2, denominator degree, which is 4. And what did my steps say? Step 1 said if denominator is greater, then it's y equals 0 is the horizontal asymptote, right? Which is our case here. I said if they're equal, it's A over B is the horizontal asymptote, where A and B are the leading coefficients. I said if the numerator is greater than the denominator by 1, then long divide denominator into numerator. Well, not just the D, but the whole denominator into the whole numerator, and then the answer will be up here. AX plus B will be your answer. Will be your oblique. That would be oblique. And then case 4, if the numerator is greater than the denominator by 2 or more, no horizontal oblique asymptote. All right, so there's the steps again. All right, so anyway, so what do we have? Numerator is 2, denominator 4. Denominator is greater than numerator, so y equals 0. So the horizontal is y equals 0. We good? Now, I haven't given any logical reasons for those. I want to. I don't like doing math this way. Monkey see, monkey do, right? I mean, that's silly. What is that? You know, 5-year-old could imitate that. Let's get to some logic. Why is that true? So, and that's the enjoyment of math for me anyway, is the way things work logically, what's true, not just memorizing steps. So, why is that true? Why that whole thing? Well, think about it. When you're thinking about, first off, let me reason with you. When you're thinking about a vertical asymptote, what does it mean to be a vertical asymptote? It means the graph rockets up or rockets down one side or the other, both sides, you know, of the vertical line, right? That's what it means to be a vertical asymptote. So rocketing up or a rocketing down at that x location. Well, what? You got a fraction here. What can I do to a fraction to make it go to infinity? Tell me, guys. 7 over 3. What's that? 2. 2 1/3, you know. What can I do to make it go to infinity? Well, you could make the top number just go to infinity. That's one way, right? But the other way is to make the bottom get closer and closer to 0. Do you realize that? If the bottom of a fraction gets close to 0, the overall fraction blows up to infinity. What am I talking about? Let's make sure. You really want to catch these things. This is the stuff. You know, if you want to go into the world of math and science, what I'm doing right now with you is what you want to learn to do for yourself more and more. Math and science is not about memorizing. I never could have made anything in that world if it was about memory. It's about bad memory. It's about logic. It's about getting it. So get it with me for a minute. Think about this. If I go 10, let's go 20. 20 over 10, that's 2. 20 over 5, that's 4. 20 over 2, that's 10. 20 over 1, that's 20. Look, as the bottom gets smaller, the answer gets what? Bigger, of course. Right? The top isn't changing. Top's 20 in all those cases. Right? If you have a fraction where the top is not changing, but the bottom gets smaller and smaller, then it goes into the top more and more, doesn't it? So what if you go to fractions now? 20 over like 0.5. Well, however much, you know what we're really saying is, how many $1 bills in 20 bucks? Well, 20. So how many 50-cent pieces in $20? Well, twice as many, because there's 2 50-cent pieces in every dollar. So it'd be 40, right? Well, how many dimes? 0.10, right? Dimes. I'm making the bottom smaller and smaller. The bottom's headed to 0. How many dimes? Well, there's 10 of them in every dollar. Times 200 now, right? Do you see that? Do you see as the bottom heads to 0, the whole thing blows up to infinity, right? Well, in other words, when a function is blowing up to infinity, and negative infinity is the same thing, you just throw a negative sign in front, right? Positive or negative infinity. What that means is whatever makes the denominator 0. That's why that's what we do for vertical asymptotes. We say, hey, denominator, where are you going to hit 0? That's where the thing's going to blow up or blow down, right? Okay, now how about that's the logic behind the vertical. How about the horizontal? Let's talk about the horizontal now. What's going to make a horizontal asymptote? Well, that means as the function goes right forever, not up forever. Now we're talking about right, or maybe left, same thing, whatever. let's just talk about right forever, from above or below, whatever, it levels off at a certain height, maybe 2 or 3 or 5 or whatever, right? That's what it means to be a horizontal asymptote. As you know, again, the key phrase is as you go right, or maybe left, right forever, not up forever, right forever. So that means as x goes to infinity, not y. We're not going up forever, we're going right, or maybe left, forever, right? So you're really asking the question, what's going to happen to this fraction as I let x be really big numbers, like 1,000, a million, a billion, etc.? What's this fraction going to do? Well, do you see it's all about the relative power of the top and the bottom, right? Whoever's more powerful is going to win. It's a tug-of-war between the numerator and the denominator, right? So if I plugged in 1,000 squared over 1,000 to the 4th minus 16, I just plugged 1,000. I'm just saying, hey, way over at 1,000, what's that fraction going to do? Well, can you tell? The top's going to be 1,000 times 1,000, which is a million, right? The bottom is 1,000 to the 4th. It's a million millions. What's that? A trillion. The bottom is a trillion. Minus 16. That's like saying, national debt. Oh, we're having trouble? I'll contribute $16 out of my wallet this year. Right? It's just nothing, right? So a trillion minus 16 on the bottom. So in other words, the bottom is gigantic, right? The bottom is 1 trillion, basically. The top is just a million. Even a million paid on the national debt, sadly, at this point, it's not making much of a difference. So a million over a trillion, that's basically zero. Do you realize that? The bottom is overwhelming the top. And we're only at 1,000 right now. Let alone get to a million, plug in a million or a billion or a trillion as the x value, to the 4th power. The bottom is going to win the tug-of-war eventually. It's just going to grab that function and pull it to the ground. Right? It's going to, right, because you can cancel this. How many times does a million go into a trillion? A million times. It's basically 1 over a million. Well, except for the 16. It's basically 1 over a million. It's 1 millionth. It's at a height of 1 millionth. At x equals 1,000, it's at a height of 1 millionth, basically. It's already flattening out, isn't it? So do you see, that's why I say if the denominator is a higher power, it's going to be y equals 0. It's going to be the horizontal line at y equals 0. It's going to flatten the graph off as you go to the right or the left forever. Negative infinity would be the same thing, right? Whereas if they're equal, if they tie in their tug-of-war, then it's just going to be, they're just going to basically cancel. If this was x to the 4th up here, if this was x to the 4th, they'd basically cancel, and then it would just be the numbers in the front. Again, the 16 matters not as you plug in really big numbers like 1,000, a million, a billion. You getting the idea? You got to keep that in your mind. For horizontal, it's as you go to the right forever, as you plug in 1,000, a million, a billion. So the 16 doesn't matter. It's basically x squared over x to the 4th. And if they were the same power, so the coefficients still matter though. You might think, well, yeah, why you say the 16 doesn't matter, Mr. Aaron. What if there were numbers in front? And what if this was x to the 4th, right? Why don't we just say the 2 and the 7 don't matter either? No, they're multipliers. That does matter, right? If we take the national debt, whatever it is, trillions, whatever trillions, and we just pay $16, like I was saying, that does nothing. But if we multiply by 2, yeah, that does something, right? Multiplied numbers matter, don't they? See the difference? Add and subtracted numbers are nothing. But yeah, so it just becomes 2 7s if they were the same power, right? That's why we say that. And then what if the numerator is bigger? If the numerator is bigger, then he's going to win the tug-of-war. What if it was like x to the 5th over x to the 4th? Right? Then he's going to win the tug-of-war. Plus, whatever, blah, 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 plus whatever. He's going to win the tug-of-war, but barely. Only by 1 degree. So it's kind of like they cancel and you get x to the 1st power. It's not exactly that. You technically have to long divide, like I said in the step, to see what it really is. But it's going to be an mx plus b kind of thing. I called it ax plus b, but same thing. It's going to be linear. Meaning, as you go off to the right, this is getting to be a mess. Let me get a fresh screen. I just scribble all over it. Yeah, so again, if the numerator is bigger than the denominator by 1, say you've got like 7x to the 5th plus, blah, 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 over 3x to the 4th plus whatever, then it's going to affect, as you plug in, 10, 1,000, a million, a billion, way off to the right forever. It should go way over here. It's going to go up like 7x over 1, right? This will reduce. Kind of like, not exactly. You got a long divide to get exactly what it is. But roughly, it's x to the first power. Meaning, as you go to the right forever, it's going to go up like a diagonal x to the first power, mx plus b line. Does that make sense on that? It's linear. And then the last case, if the numerator is bigger than the denominator by 2 or more, that'd be like 7x to the 6th over 3x. The numerator is just going to dominate the scene. It's going to blow up to infinity. As you go to the right, it's just going to rocket up, or if there's a negative sign, it'll rocket down. It won't have any horizontal or diagonal asymptotes. All right, so there's the logic. Glad to talk to you more about that. If try it. All right, so there we go. So let's start with the vertical asymptotes on number 17. Let me let you try that. Was that going to be a factoring thing? Yeah, you know what? I don't have time to give you lots of time to factor because I got to get through these problems. So I encourage you to do that on your own, but I'm just going to do it quick here. Right, plus 1 minus. Yeah, that's all right. You can check it if you want, but it's right. And then something 20 and 2, huh? 4 and 2 minus plus 2 minus 20. Right, that's right. So I just factored them both, and this one does have a reduction, doesn't it? So this is one of the cases where we need to. So then, so step 1 is factor reduce. Step 2, denominator. Now we only use the 5x plus 2. That's all we use, equal to 0 to find the vertical asymptote. Move the 2 over. Minus 2 divided by 5. There it is. X equals negative 2/5. That's the vertical asymptote. Is that good? Let me move ahead. I'll flash back. That was probably quick, I know. You guys all got that down there, okay? X equals negative 2/5. All right. I'll move ahead. And now let's find the vertical. No, that was a vertical. Horizontal oblique asymptotes. All right, how do we do it? Numerator degree, denominator degree. Let me let you do it real quick. So just think about it. For horizontal, just think, if I plugged in 1,000, a million, a billion for x there, top and bottom, what would happen? All that would matter is these most powerful terms. Everything else would fade into nothingness, right? If you plug them, even just 1,000 squared is so much bigger than just plain 1,000, right? 1,000 is 1,000 squared. It's 1,000 thousands. It's a million. So anyway, so all that's going to matter really is 2x squared over 5x squared. That's what we're really doing with this horizontal thing, horizontal oblique thing, is we're just looking at the most powerful term. Because that's all that matters as you go off to the right forever. It's the most powerful term on the top, most powerful term on the bottom. They're going to effectively cancel. It's going to be 2/5, isn't it? Because they're both 2. They equal each other, and so it's just y equals 2/5. Make sense? It's a horizontal asymptote. Y equals 2. It's going to level off at 2/5, right? On the graph, you know what I mean by that? This is 1, this is 2. 2/5 is what? A little below a half. I looked like I went above a half, but it's supposed to be a little below a half, right? 2/5 is 0.4, right? 0.4 on the graph. Which means this graph is going to do something like that or something like that. I don't know which side it's going to come from, but it's going to do something like that. It's going to do the same thing on the other side. It's going to level off at 2/5, 0.4. Good questions? Oops. Okay, so let's start with the vertical. So you got to factor that. I don't think that top's going to factor. Does it? Maybe it does. Maybe you're right. Yeah, oh yeah, you're right. Plus and minus. I plus 28 minus 21. Yep, you're right. Oh, that's interesting. So bang. So There's no denominator, so no vertical asymptote. Yeah, they're trying to trick us. That top does factor. Yeah. So no vertical. So you got to reduce that. No vertical. So let's go on to the horizontal oblique. I'll flash back. I know I'm going quick here. So make sure I cover it. You guys got all that down? So it does factor. 3x plus 7, 4x minus 7 reduces. No denominator, no vertical asymptote. Okay, so let's do the horizontal oblique now. And just think about the most powerful term in the top and the most powerful term in the bottom, because that's all that matters. Smaller terms added and subtracted to them don't matter at all as you plug in gigantic numbers like 1,000, a million, a billion. So what's that going to basically do? Reduce and be like 4x. Now, it's not exactly 4x, but it is linear. That is telling me, oh, it's y equals mx plus b, or ax plus b, whatever you want to call it. Right? It's linear, meaning as you go off to the right forever, as x heads towards positive or negative infinity, it's going to go up like a line. It's not going to go up like a rocket. It's not going to go up curved, and it's not going to level off. It's going to go up like a line, because the numerator is 1 degree higher than the denominator. He's going to win the tug of war, the top is, so he's going to pull it up forever. Right? The top's trying to pull out, the bottom's trying to pull down, right? The numerator will pull it up, but not dramatically, only in a straight line. Right? So now I've got to find the equation of that line, and it's not just 4x. That's just a quick help to me to go, oh yeah, it's an oblique. It's a diagonal. Now, how do you find it? How do you actually find the oblique? You got to long divide, and it might have been a long time since you've long divided algebraically. So number one step then is numerator is 2, denominator is 1. Numerator is greater than denominator by 1, so it's oblique. It's diagonal. So now how do we find it? You go denom into numerator. So let's do that. So you got to take the 3x plus 7 into the 12x squared plus 7x minus 49. Now I know this can be a little bit weird. So it's front to front. Remember how long division works? Just like normal number long division? Right? Think about 21 into 87. What would you do? You just go, what can I put up here? Times 2 that'll make 8. You go 4. Right? And then what you would do in numbers? And then you would multiply that 4 only times the 2? No, times both, which would be 84. And then you would subtract, right? Same thing here. What can I put up here? Times the 3x, that'll match the 12x squared. 4x. Same exact thinking, right? So 4x. What do you get? Now, does it just multiply the 3x? No, it multiplies both, just like that 4 multiplied both, right? So 4x times 3x, 12x squared. 4x times 7, 28x, right? Draw your lines, subtract them. 12x squared minus 12x squared, gone. 7x minus 28x is minus 21x. Bring down the minus 49. Just normal long division, but letters everywhere, right? All right. What's the next step now? Let me clean this up a little bit. So now we go to the part here. What times this will match this? And you want an exact match at first. Same sign, same everything. Because then when you subtract, identical things will be 0. So I want negative 7 is my point. Because you want an exact match. Same sign, same everything. Negative 7, and it'll go to both. So that will be, you write it down here, negative 21x. Negative 49. Perfect. Look at that. Subtract that, it's 0. See how you had to make the same sign? So they subtract, right? If that was a plus 21, if I'd used plus 7, then negative 21 minus 21 would have been minus 42. That's not what I want. I want 0, right? Not that you always get 0. You don't always get 0. But you try, at least the front part's got to be 0. The front part's got to be made 0.
No, I mean, it doesn't end 0.
Yeah, I don't care about the rest because I don't. If there was another part like a number 7 or 10 or whatever over here, it would just be the remainder, and I don't care about the remainder because I have what I need. I have the ax plus b or mx plus b, whatever you want to call it. So it's y equals 4x minus 7. So we were right about the 4x, but it's 4x minus 7. That is the oblique asymptote. Y equals 4x minus 7. That's a line. That's an mx plus b, right? That's a line of approach. The graph, if you were to graph this thing, go to new screen here. Did I do that too quick? Did you guys get that down? So if you were to go to a new screen and graph that, you would graph the line y equals 4x minus 7, and the graph would approach it. It'd be a guideline for the graph as it goes off to the right forever. So I could say 4x minus, what 4x minus, it was minus 7, wasn't it? Yeah, minus 7. So go down 7, 4, 5, 6. So you don't have to do this, but I'm just showing you. Minus 7, then go up 4, 1, 2, 3, 4 over 1. So, whoops, supposed to be dotted, huh? So there's our asymptote line. And that means the graph, as you go off to the right forever, I didn't draw it really very well. There you go. As you go off to the right forever, the graph is going to approach that line. That's what that means. It might do it from the bottom. I don't know what it's going to do exactly, but it's going to approach that line. Is that good?